Okay, thank you. My name's Shaun Earl. I'm from the Advanced Metallic CDT at the University of Sheffield, which means I'm a metallurgist, which means I'm going to be showing you a lot of micrographs. I apologise if you're not a big fan of them. And I'm going to be presenting to you some of the initial results of an ongoing project into squats and studs. Now, I've been using CT scanning to help to aid in trying to characterise squats and studs even better. So I'm going to spend a little bit of time talking about CT scanning, just to introduce you if you're not familiar with it. Then I'm going to move on to how I verified and how accurate the scanning is, before I then talk about a couple of the interesting features in a few of the samples. The samples I'll be talking about are studs, and then I'll be making some remarks at the end. Okay, so I started out using the Alacona infinite focus microscope to map out the surface, because ultimately I'd like to be able to create a link between what you see on the surface and what's actually under the surface. The big question then was, well, where do I cut, where do I section, where are the interesting things that I need to be looking at? So in order to make a bit more sense of what is on the surface, what it means under the surface, I turned to CT scanning. CT scanning has been used before, but rather than doing a very small area, I wanted to try and scan the entire defect, so we needed a very big scanner. So this is where the 450 kilovolt hutch at Muvis in Southampton came in. Just to run through quickly how it works, so in the X-ray gun, you use a high voltage to create a thermionic reaction, generates a beam of electrons, which crash into a reflection tungsten target, creating a polychromatic beam. This beam travels through your sample, which it sits on the rotational stage. The stage rotates so that the beam is passing through at multiple angles. It can also move in the X, Y, and Z axes. The resultant photons or X-rays are then detected by the detector, and the software is able to reconstruct the volume. Now, the reason I mentioned polychromatic beam, this means that, for example, we were typically using around about 400 kilovolts. This is the peak voltage, so it means that you've got rays of multiple different energies. So some of the rays will be absorbed by the sample, and this creates effects within the sample that I'm not going to go into, but what it means is sometimes what you see in the scan might not be real. Because of this, it's necessary to verify the scans. So at the top here, you have a false color image of one of the scans. And as you can see from the unetched micrograph below, it is very much similar. It hasn't picked up on all the detail due to the low resolution, and that's to do with the very large sample size that I put in, because it was a full rail width. But generally what it was picking up on was real, and what you're seeing between the three pictures is that consistent hole which actually breaks the surface. So, looking good. So what about this one? We've got a very large shadow in the middle. This could be streaking. This could be a scattering effect due to the fact there's two cracks very close to each other, and this is what I assumed. Unfortunately, it is real. This is in the rail. I haven't run XRD on it yet, but I will be running XRD to find out what elements are actually inside there. And I believe this is very close to where the initiation took place. So this is a model of one of the samples. The red represents what the automatic crack detection software was able to see. The blue is then what I had to manually go through and add in myself, because due to noise, etc., the software can't see everything. So as you can see, you've got your main crack at the top, and then you do have a crack below that, but it isn't traveling deep, it's just traveling just underneath the other one. And in a moment, some green will turn up. The green corresponds to the yellow on the surface of that rail, so that will then give you an idea of how what you see on the surface corresponds to what's underneath, and the deepest points are generally in the middle of the running band, but I believe the initiation took place where the Y-shaped crack was on the field side. Okay, so looking at the running band a little bit more, I see from the top image you've got quite a lot of vertical cracks, so this is because of large thermal input. It's the sudden cooling due to the massive heat sink of the rail that then causes large tensile stresses that cause these vertical cracks to appear. You do have some cracks as well which effectively go down a little bit and then resurface quite quickly, and I often found little islands of white etching layer along with these. And you can see there's also an isolated crack down in the bottom right corner, but this could be connected to another crack in a different direction, so it doesn't mean it is isolated as such. The bottom right-hand corner just shows another vertical crack, quite a large one, just on an etched image, and you'll notice the grains are quite highly refined, showing that, again, it has suffered thermal damage. In the bottom, I've highlighted a little area in orange. This is the image that was verified earlier. And you can see where the cracks have started to grow through the structure, and this is 100 times magnification, and you can barely see the grains. So again, it's showing what the thermal damage is doing. And you can see how the crack would naturally like to continue to follow this ferrite that's segregating out due to the thermal damage. So this is why I believe studs are growing faster than squats, because these natural pathways are making it very easy for the cracks. This is something slightly different. So this is decarburization on the gauge corner of this sample. The interest in this is because if I can work out what kind of parameters would be necessary to create this level of decarb, it'll give an idea of what kind of environment the rail was suffering at the time of most of this damage being caused. And the only reason I actually found, time's slightly in the way, but the only reason I actually found this was because within the CT volume there was a streaking effect, and I wanted to see if that was real or not. And I found decarb where I wasn't actually expecting to find it. I should mention this sample is from an incline heading in towards the station, so the train will have been braking. The last slide on this sample. So again, just to give you a bigger image of the type of marker structure I'm typically finding at the surface of the rail. 50 microns below this image, you've then got what the structure should look like. You should be able to see the nice pearl-like colonies. They should have nice clear grain boundaries, but clearly this isn't the case. And as well as being a very refined structure and a somewhat distorted structure, there's also a loss of material at the surface. This could possibly be due to white etching layer that's broken away during the sample preparation process. So this is the raw data. This is what I see when I first get the volume. And what you're doing here is you're seeing the rail from a longitudinal direction, and you're traveling from the field side through to the gauge side. You'll soon see the triangular shadow that I showed you earlier. But what is worth taking note of is you'll get glimpses of something much deeper down. So you've got the typical defect, you seem to have another one further along, and then there's a crack growing downwards. Now this area, because it wasn't particularly clear in this scan, this was actually cut out as a much smaller piece to then scan again as a higher resolution scan. And I'm just working through that at the moment just to verify how many cracks are there and how serious they should be taken. And just as a finishing note, this is just showing how the surface of this rail, both within the defect and outside the defect, is showing localized lamination. There's some grinding marks as well, and it's work in progress, but I'm currently looking at linking the surface damage to areas of very high damage subsurface. So again, showing the importance of good quality surface finish. Here we're taking another look at vertical cracks within a different sample, and here you can see the vertical crack starting at the top, but it's also growing up towards it from the bottom as well. And zooming in on the crack, that crack's actually cutting across grains. Now with a typical squat, you'd expect it to follow the ferrite around the grains because it's easier, but because of the thermal damage, it's cutting across the grain instead. So here I've got another model. Now this one's showing another sample. Now this sample was a lot thicker because unfortunately before the allotted scan time I was unable to get through it without I didn't want to create too much heat input. And so what was automatically detected wasn't quite as high as what was detectable on the other one. But generally speaking, these defects somewhat simple in terms of it doesn't branch much, and that would probably just end up shelling away eventually. The initiation site, which is towards the centre, which again correlates to the yellow, is on the very edge of the weld. So that's something I took an interest in because I believe this was the initiation point, with the other crack just being where the crack broke out on the edge. So looking at the initiated site, I did do a hardness map to try and see if there was a very big hardness variation. Because if there was a big hardness variation, it could have been differential wear, but there was no significant variation. The weld was generally typical as I would expect. The mag structure did vary a little bit here and there, but nothing that I thought would cause it. But when I did take a closer look just underneath the initiation site, I did find gas bubbles within the weld, So the center image is the unetched version. The far side is an etched version, and the one above it is just from somewhere else within the same sample, but just to show that it's not etching effects or anything like that. These bubbles are fairly consistent along this weld line, just under the surface. They're not continuous down through the sample. They are just sitting in a very localized area. Okay, so just to summarize what I've been through. The vertical cracks were found due to thermal damage. Now, I found these cracks fairly consistently. They don't show up particularly well in CT scanning just because of the edge hardening effects, making the surface look much more dense than it actually is. Samples 1 and 2 initiated on the field corner. This makes me believe that hollow wheels are possibly responsible here. Sample 2, this is jumping ahead slightly because I have seen the higher resolution image. That crack does appear to be growing downwards. It's still incredibly small at this stage, but its direction is heading downwards, growing in from the field side, not developing within the centre of the rail. Sample 4 failed due to the gas bubbles, and the overall extent of thermal damage varied not only from sample to sample, but even from one side of the running band to the other. In some areas, you could have 400 microns deep of thermal damage. You could have quite a large amount, and then in other areas you'd have maybe only 40, so it could be very minimal. So thermal damage is varying, so possibly different contact areas. And with regards to a comment to the CT scanning and how useful it is, when done at higher resolution, you do get a much better image, but generally speaking, for mapping out a defect, it was effective. It allowed me to pick up on areas that I wouldn't normally have looked at. It allowed me to find things within areas I wouldn't normally see. And because I was able to build the 3D model, it's a little bit easier to trace your crack planes back to where they initiated from. Because obviously once you normally chop through a rail, you can't then go, it's a bit difficult to look elsewhere. But if you built a 3D model, you can just follow that crack path through the volume back to where it came from, making it a little bit easier. Like I say, this is ongoing work. There is a higher resolution model being built, and I'll be taking this a little bit further. Thank you very much.
Thank you for your presentation. I'd like to ask you if there are any plans to check the outcomes of your technique with the typical results of the indications given by the current systems or ultrasonic systems in order to get something that is comparable between conventional techniques and this technology. Thank you very much.
Yeah. It would be good to be able to do something like that, especially because they are both obviously penetrating it. That would generally be dependent on if I could get hold of ultrasonic data to provide comparison. But if I could get hold of such data, and if anyone has such data they'd like to share so that I can compare it to what I'm seeing through these models, that would be excellent, yes.
Thank you for a very interesting presentation. I've got a question. You showed this sawtooth-shaped crack on one of your slides. I think it was specimen 2.
Okay.
Do you have any idea why this crack formed like this, or any theory?
Yes, where there were multiple surface cracks. I believe I don't know if can I cycle back in this? Yes, I'll nip back a bit. I believe you're on about this one?
No, the next one. Next slide.
Oh, right.
Check.
This one? Yeah. So why there's so many along the surface?
No, the question was this sawtooth-shaped crack on the right-hand side.
The one below it?
This one,
yes. Yes, this is something that I found in a couple of places. So there seems to be much straighter cracks, which are typically thermal damage, but then you have this saw-like effect due to cyclic loading on and off, which is much more mechanical. And what I'm looking for microstructural sensitivities, and when it seems to be more thermally caused, it just seems to travel in very straight lines with no regard for the microstructure. But then there's also places where it will work its way around the grains and it'll take the easier path, as squats typically do. So it's not simply that all these cracks are caused by thermal damage, there is the mechanical load inside to it as well. Does that answer your question? Yeah.
I think so.
Thank you.
Okay, thank you very much.